Now to prove that it is true for P of k plus 1, just for this add k plus 1 whole square on both sides of equation number 1. 2 to the power of 2n minus 1 is divisible by 3 when n is equal to 1. That means the statement is true for n is equal to 1. First part. So here very important concept is let the statement is true for n is equal to 3 and then prove that it is also true for some positive integer k. Hello dear students, welcome to this session of Discrete Mathematics Revision class. I am Mr. Niranjan, Faculty Department of Computer Science, Vidhyaashram First Grade College, the Temple of Excellence. So in my previous class, we have discussed regarding the problems on binomial theorem as well as the problems on mathematical induction. Today in this session, I will take few more problems on mathematical induction and some problems on recurrence relation, right? Now let us move on to the first problem. This is also very important for the point of examination. So in mathematical induction, you will get two questions. So for 15 marks, you will get two questions. One is 8 marks, another one is 7 marks. Already in the previous class, we have discussed some problems. Let me take few more problems based on this. Now the first one is, this is a 7-mark question. Prove by the method of mathematical induction that 1 square plus 2 square plus 3 square plus etc. n square is equal to n into n plus 1 into 2n plus 1 by 6 for all n belongs to n. So this is an important problem. You may expect this for the examination. Now let us write this as P of n. The given equation can be written as let P of n is equal to, this is 1 square plus 2 square plus 3 square plus etc. n square is equal to n into n plus 1 into 2n plus 1. As usual procedure, let us prove the statement for some, as usually prove that the statement is true for n is equal to 1. Again prove it for some positive integer n is equal to k. Then show that it is also true for P of k plus 1. That's all. Now let us write to prove that, put n is equal to 1. Put n is equal to 1, then P of 1 can be written as, here this is 1 square is equal to 1 into 1 plus 1. 2 into 1 is 2 plus 1 divided by 6. 1 square is 1. 1 into 1 plus 1 is 2 into 2 plus 1 is 3 divided by 6. 2 3s are 6 gets cancelled. 1 is equal to 1. That is LHS is equal to RHS. That means therefore P of n is true. P of n is true for n is equal to 1. This is the first part. That's it. Put n is equal to 1 and show that LHS is equal to RHS. Hence concludes that P of n is true for n is equal to 1. To prove that the statement is true for some positive integer k. Now we know that P of n is equal to 1 square plus 2 square plus 3 square plus etc. plus k square is equal to n into n plus 1 into 2n plus 1 divided by 6. Now to prove that P of n is true for some positive integer n is equal to k, then this becomes P of k is equal to 1 square plus 2 square plus 3 square plus etc. plus k square is equal to k into k plus 1 into 2k plus 1 divided by 6. Let us represent this as equation number 1. Now to prove that the statement is also true for P of k plus 1. Now to prove that it is true for P of k plus 1, just for this add k plus 1 whole square on both sides of equation number 1. Just add, so that is P of k implies 1 square plus 2 square plus 3 square plus etc. plus k square. We are adding k plus 1 whole square on both sides of equation number 1, k into k plus 1 into 2k plus 1 divided by 6 plus 1k plus 1 whole square. Take LCM, 6 is the LCM, just 6 is the LCM, k into k plus 1 into 2k plus 1 plus cross multiplied 6 into k plus 1 whole square. You can take the common factor. What is the common factor? K plus 1 is the common factor, k plus 1 is gone. What is remaining is k into 2k plus 1 plus here 6 into 1 k plus 1 is gone and 1 remaining k plus 1 divided by 6. Now just simplify this. So if you simplify, what you will get? So this is equal to k plus 1 as it is. Now multiply 2k into k is 2k square plus k into 1 is k plus 6k into 1 is 6k plus 1 divided by 6. Okay. Now therefore this can be written as this is equal to k plus 1 into 2k square plus 7k plus 1 divided by 6. So if you factorize this, what you will get? Factorize this. Okay, let me explain this first. To prove that p of n is true for some positive integer n is equal to k, put n is equal to k, then we will get 1 square, 2 square, 3 square, etc. K square is equal to k into k plus 1 into 2k plus 1 by 6. So that means p of k is also true, p of n is also true for some positive integer n is equal to k. Now to prove that it is true for p of k plus 1. So for that, add k plus 1 whole square on both sides of equation number 1. So what happens? P of k is 1 square plus 2 square plus 3 square etc. plus k square plus k plus 1 whole square is equal to k into k plus 1 2k plus 1 by 6 plus k plus 1 whole square. Take LCM. 6 is LCM. Cross multiply. 6 into k plus 1 whole square. Here you can take k plus 1 common factor. K plus 1 is gone. K into 2k plus 1 plus 6 into 1k plus 1 multiplied. So k into 2k is 2k square plus k, 6k plus 6, that is 2k square plus 7k plus 1 divided by 6. So what we got? K plus 1 into 2k square plus 7k plus 1 divided by 6. Okay. Now let me go to the next page. Now again, now therefore p of k is equal to what we got? So 1 square plus 2 square plus 3 square plus etc. plus k square plus k plus 1 whole square is equal to, we got k plus 1 by 6 into 2k square plus 7k plus 6, right? Okay. Now factorize this, that's all. Factorize this. 2k square plus 7k plus 6 can be factorized as, so you can take 2k into k, this can be written as 3 into 2. If you multiply, what you will get? Plus 3k plus 4k, that's equal to the middle term plus 7k you will get, we can put. So the factors are k plus 2 into 2k plus 3. So therefore this can be written as k plus 1 into, here it is k plus 2 into 2k plus 3, 2k plus 3 divided by 6. Now this can be written as k plus 1 into, what are the factors we got? K plus 2 into 2k plus 3 divided by 6. So this can be written as k plus 1 into k plus 1 plus 1 into, this can be written as 2 into k plus 1, 2k plus 2 plus 1. So divided by 6, equation number 2, right? Okay. Now if you observe carefully from equation number 1 and 2, wherever there is k in equation number 1, we have k plus 1 in equation number 2. So therefore p of k plus 1 is also true, So hence by induction, therefore hence by induction p of n is true for n is equal to 1, and p of k is true implies p of k plus 1 is also true, therefore p of n is true for all n belongs to n, that's it. So this is how we are going to verify. If you do this much, definitely you will get a 7 marks, that's it. Hope you followed. Okay, this is by the method of mathematical induction. Now move on to the next problem, problem number 2. Using the principle of mathematical induction, for all n belongs to n, prove that 2 to the power of n minus 1 is divisible by 3. This is also an important type problem. So you may expect this type of problems also. Now just very simple, we have to show that 2 to the power of 2n minus 1 is divisible by 3. Now very simple method, same. Let the statement represent the given statement as p of n. The p of n is nothing but the given statement p of n is equal to 2 to the power of 2n minus 1 for all n belongs to n. So 2 to the power of n minus 1, that is p of n is equal to 2 to the power of 2n minus 1 is divisible by 3 for every natural number n. Suppose if you put n is equal to 1, put n is equal to 1, then p of 1 is true. That is, p of 2 to the power of 2 into 1 is 2. So that is p of 1. P of 1 is 2 to the power of 2 into 1 is 2 minus 1. 2 square is 4 minus 1 is equal to 3. So this can be written as 3 into 1. That means this 2 to the power of n, 2n minus 1 is divisible by 3. That means the statement is true for n is equal to 1. Assume that. So therefore, p of n is true for n is equal to 1. For n is equal to 1. Very simple. See, same procedure. Just prove that the statement is true for n is equal to 1. Put n is equal to 1. If you put n is equal to 1, 2 to the power of 2 into 1 is 2 square. 2 square minus 1. 2 square is 4. 4 minus 1 is 3. So 3 is divisible by 3. So that means this can be as 3 into 1. So therefore, 2 to the power of 2n minus 1 is divisible by 3 when n is equal to 1. That means the statement is true for n is equal to 1. First part. Second part. To prove that the statement is true for some positive integer k, put n is equal to k. Assume that p of n is true for some positive integer k. That is, p of k is equal to 2 to the power of 2k minus 1 is divisible by 3. Now that is 2 to the power of 2k minus 1 is equal to 3 times q, where q belongs to any natural number. Now to prove that p of k plus 1 is also true. Now how to prove p of k? Put k is equal to k plus 1 in this case. So p of k plus 1 is equal to 2 to the power of 2k plus 1 minus 1. So multiply 2k into 1 is 2k, plus 2 ones are 2, 2k minus 2 minus 1. You know, according to law of indices, a to the power of m plus n is also equal to a to the power of m into a to the power of n. So this 2 to the power of 2k plus 2 can also be written as 2 to the power of 2k into 2 to the power of 1. According to law of indices, a power m plus n is a raised to m into a raised to n. This 2 to the power of 2k plus 2 can also be written as 2 to the power of 2k into 2 to the power of 2. So 2 to the power of 2k into 2 to the power of 2 minus 1. What is 2 square? So 2 to the power of 2k into 2 square is 4. So 2 square is 4 minus 1. So this 2 to the power of 2k plus 4 minus 1 can also be written as 3 into 2 to the power of 2k. Just add 2 to the power of 2k minus 1 on both sides. So then this becomes 3 into 2 to the power of 2k plus 2 to the power of 2k minus 1. Since this 2 to the power of 2k minus 1 is also equal to 3q. So 3q can be written as 2 to the power of 2k minus 1. Substitute here 3 into 2 to the power of 2k plus 3k, 3 times q. So this is 3 into 2 to the power of 2k plus 2 to the power of 2k minus 1 is equal to 3q. So just take 3 common factor, 3 into 2 to the power of q. Just take 3 common factor. If you take 3 out, then this can be written as 2 to the power of 2k plus 3 is gone q. So 3 into 2 to the power of 2k plus q is equal to, call it as m, where m is equal to 2 to the power of 2k plus q, where m belongs to any integer, and therefore this implies that p of k plus 1 is true whenever p of k is true. That means, hence by the principle of mathematical induction, that p of n is true for all n, So hence by the principle of mathematical induction, p of n is true for all n. So this is an important step here, right? Now let us move on to the similar type problem. One more problem is there. Using the principle of mathematical induction for all n belongs to n. Now let us take similar type problem. This is also a very important problem. Using the principle of mathematical induction for all n belongs to n, prove that 2n plus 1 is less than 2 to the power of n. 2n plus 1 is less than 2 to the power of n for all natural numbers n which is greater than or equal to 3. Greater than 3 or equal to 3. Now let us assume that as p of n. Let p of n is equal to, p of n is a given statement, that is 2 to the power, p of n is equal to 2n plus 1 which is less than 1. Now put n is equal to 1 as usual. Let us just represent the given statement as p of n. Now the given statement p of n is 2n plus 1 is less than 2 to the power of n. Here we cannot take n is equal to 1 because it is already given. N should be greater than or equal to 3. Let us take n is equal to 3. Put n is equal to 3. For all natural numbers n is greater than 3. So just put n is equal to 3. If you put n is equal to 3 here, then what happens? this becomes P of 3 is 2 into 3 plus 1 is less than 2 cube. So 2 into 3 is 6 plus 1 is less than 2 cube means 8. So that is 7 is less than 8. So 2 into 3 is 6 plus 1, that is 7 is less than 8, that is 2 cube. That means P of n is true for n is equal to 3. Right. Next, assume that the statement P of n is true for some positive integer k. So that is 2k plus 1 is less than 2 to the power of k. And to prove that this is also true for P of k plus 1. Right. So here very important concept is, let the statement is true for n is equal to 3 and then prove that it is also true for some positive integer k. Then prove that it is true for P of k plus 1. Now, just we have to show that 2 times k plus 1 is less than 2 to the power of k plus 1. That's it. Now, just now we have 2 into k plus 1 is equal to 2k plus 3. 2k, 2 into k is 2k plus 2 ones are 2 plus 1, that is 2k plus 3. So, 2k plus 1 plus 2k plus 1 plus 2, 2k plus 1 plus 2 is less than 2 to the power of k plus 2, which is less than 2 to the power of k into 2 to the power of 1, which is equal to 2 to the power of k plus 1 here. So we have 2k plus 1 plus 1. This 2k plus 1 can be written as 2 into k is 2k plus 2 plus 1, that is 2k plus 3. So 2k plus 3 can be written as 2k plus 1 plus 2, 1 plus 2 is 3. This is less than 2k plus 2, which is less than 2 to the power of k into 2 to the power of 1 is 2. So 2k into 2, that is nothing but 2 to the power of k plus 1. That means P of k plus 1 is also true when P of k is true. Hence, by the principle of mathematical induction, P of n is true for all natural numbers n is greater than or equal to 3. That's it. This is how we are going to prove this statement. Okay, hope you followed. These two problems are very important also. Now move on to the next concept, that is a recurrence relation. Let me define some problems on recurrence relation. Okay. Now let us take straight away, these are 5 marks question. Define the sequence a1, a2, a3 as defined. This is defined as a1 is equal to 2, an is equal to 5 times an minus 1 for all natural numbers n is greater than or equal to 2. Write the first 4 terms of the sequence. Now here n is greater than or equal to 2. So n is greater than or equal to 2 means put n is equal to 2, n is equal to 3, n is equal to 4, 5 and 6. Now what is given? a1 is equal to 2. Then an is equal to 5 times an minus 1. Put n is equal to 2. If you put n is equal to 2, a2 is equal to 5 into a2 minus 1. That is 5 into 2 minus 1 is 1. So that is 5 into, what is a1? a1 is 2. 5 into 2 is 10. So the sequence is, first it is already given 2. We have a1 is 2 and a2 is equal to 10. Now put n is equal to 3. If you put n is equal to 3, then a3 is equal to 5 into a3 minus 1. That is 5 times a2. 5 into, what is a2? 10. 5 into 10, this is equal to 50. Next, n is equal to 4. We put n is equal to 4, a4 is equal to 5 into a4 minus 1. That is a3. 5 into a3. What is a3? a3 is equal to 50. 5 5s are 25. This is equal to 250. Right. Now, if you take n is equal to 5, then a5 is equal to 5a5 minus 1. That is 5a4. That is 5 into a4 is 250. 250 into 4 is 1250. This is 1250. So these are the 4 terms of the sequence. So therefore, the sequence S is equal to 2, 10, 50, 250 and 1250. That's all. If you do this much, you will get 5 marks. Okay. Now, move on to the next problem. Define the sequence same a1, a2, a3 as follows. This is defined: a1 is equal to 5, a2 is equal to 3, n is equal to 3 times an minus 1 minus 2 an minus 2 for all natural numbers n greater than 2. Write the first 4 terms of the sequence same. What is given here? a1 is given, a1 is 5, a2 is also given, a2 is 3 and what is given an. An is equal to 3 times an minus 1 minus 2 times an minus 2 for all n greater than 2. Greater than 2 means put n is equal to 3, 4, 5, 6. So if you put n is equal to 3, then this becomes a3 is equal to 3a, 3 minus 1 minus 2 times a, 3 minus 2. So this is 3 times a2 minus 2 times 3 minus 2 is 1. So 3 times a2 is equal to 3 minus 2 into a1 is equal to 5. So 3 3s are 9 minus 10, that's equal to minus 1. Similarly, put n is equal to 4. a4 is equal to 3 into a, 4 minus 1 minus 2 into a, 4 minus 2. 3 into a3 minus 2 into a square. 3 into a3. What do you got? a3 is equal to minus 1 minus 2 into a2. What is a2? It is given 3. So that is equal to minus 3 minus 6 is minus 9. Similarly, put n is equal to 5. What we have? an is equal to 3an minus 1 minus 2an minus 2. So put n is equal to how much? 5. You put n is equal to 5, a5 is equal to 3a, 5 minus 1 minus 2a, 5 minus 2, 3a4 minus 2a3. So 3 into a4. What is a4? a4 is minus 9 minus 2 into a3. a3 is equal to minus 1. So 9 3s are 27, minus into minus plus 2, that's equal to minus 25. So last, put n is equal to 6. You will get a6 is equal to 3a, 6 minus 1 minus 2 into a, 6 minus 2, that is 3, a5 minus 2, a4. So 3 into a5 is minus 25, a4. What is a4? a4 is equal to minus 9. So this is equal to minus 75. Minus into minus plus 9 2s are 18. What is this equal to? Minus 75 plus 18. Now if you subtract, this is equal to minus 57. That's it. So therefore the sequence S is equal to what we got. So a1 is 5. a2 is equal to, what is a2? a2 is equal to 3, 5, 3. Then a3 is equal to minus 1, minus 9, then minus 25, then minus 57. So here what is the question they have asked is just write the first 4 terms of the sequence. That's all. We want to write only the 4 terms. Suppose if they ask write 5 terms, just write 5 terms. That's all. So these are the 4 terms, 1, 2, 3, 4. So minus 1, minus 9, minus 25, and minus 57. That's it. So if you do this much, definitely we will get a 5 marks. So you may expect this type of questions also in a recurrence relation. Right. Okay. So hope you followed. So that's all regarding today's session. Let us meet with a different concept. So in the next session, I am going to take very important problem, that is on sets, relations and functions. So you will get one full question from sets, relations and functions that I will take it in the next class. So hope you followed. That's all regarding today's session. Let us meet with the next concept in the next session. Thank you. Thank you very much.